The Washington Post reports this week that a geologist, Professor Elizabeth Turner of Laurentian University in Ontario, has uncovered fossilized structures that are identified as sponges, a primitive form of marine animal life. These fossils, found in northwest Canada, they date back some 890 million years, which would make them some of the oldest known signs of animal life on Earth. After investigating the field area for her thesis, she collected samples that contained porous skeletons. Then her findings were published just this week in the journal Nature. These skeletons cause us to think about the course of animal life on Earth. Scientists believe that life on Earth originated about 3.5 billion years ago with single-celled unicellular organisms. These soft-bodied organisms don't leave a lot of fossilized evidence. But once skeletal material became a big deal about 550 million years ago in what's called the Cambrian explosion, during a vast diversification of life, then these hard shells and skeletons gave us a great idea of what was going on. Soft-bodied early animals' origins are subject to debate because of the lack of fossilized evidence. Once skeletal materials became common in the Cambrian period, about 550 million years ago, a vast diversification of life on Earth occurred, and these early animals became more known because they're more preservable with their hard shells and skeletons. Now, if proved correct, these sponges could have existed before even oxygen was a dominant gas in the atmosphere. Maybe they had a role in helping convert that primitive Earth atmosphere to something breathable and tolerable for Earth's diversifying animals, including our ancestors. According to an article in phys.org by contributor Jennifer Chu, geologists at MIT have analyzed thousands of samples that have erupted along ocean ridges and have traced those chemical histories back to estimate the temperature of the Earth's interior. The analysis shows that the temperature of the Earth's underlying ocean ridges is relatively consistent at about 1350 Celsius, or about as hot as a pilot light or the range gas in your kitchen. There are, however, hot spots along the ridge that can reach way hotter, up to 1600 degrees Celsius, comparable to the hottest lavas that we found on Earth. The team's results, appearing this week in the Journal of Geophysical Research, provide a temperature map, if you will, of the Earth's interior around these ocean ridges. You'll recall ocean ridges are the places where spreading centers occur and new ocean floor are created. With the map, scientists can better understand the melting processes that give rise to these undersea volcanoes, and how these processes may drive the pace of plate tectonics and the motion of Earth's plates over time. In the countryside of England stands an iconic landmark, rings of ancient stones standing on end. Yes, I'm talking about Stonehenge. Scientists and historians agree that the structure was built sometime around 4600 BC by humans and heralded a spiritual center there for the Druids, which were predecessors of the modern Celtic peoples. The general belief was that the rocks were brought to this place from relatively close nearby. But from where exactly? We believe a site about 180 miles away from Stonehenge was the source of the stones. For many decades, though, the site has been protected from damage, so that prevents scientists from extracting samples from the stones and really learning more about the rock's formation. That is until the discovery of a drill core from Stone 58, taken by a driller, Robert Phillips, in 1958. Lost until 2018, the sample was made available again just recently to researchers to help peer into the history of these stones. And now we know more about them. Much more. The stones themselves are a form of siltcrete, which forms near the Earth's surface. As groundwater washes through carrying minerals, it leaves behind some cements, which bind the sediment into a form of stone. Utilizing technology like electron microscopes and X-rays, researchers have found that the siltcrete in this particular type of stone is made up of sand-sized quartz grains. The quartz grains are connected by a framework of silica cement. This quartz is the reason why, after 4,600 years, the rocks persist in the face of weathering and erosion, even today. Quartz is extremely strong and its chemicals are stable at the Earth's surface. It's hard stuff. Interestingly, there were older, larger boulders found even closer to the site. So why were these rocks mined over 180 miles away and hauled over? Why? Maybe because these rocks are hard and they're tough and they stand up to the elements and the test of time. The sediments in the stone actually were deposited in some other place during the Paleogene period, about 66 to 23 million years ago. Each of those sand grains formed as long as 1 to 1.5 billion years ago and have been reworked through time and through the earth ever since, and are now living in the stones of Stonehenge.